There we go. So it's a pleasure to introduce Jintao Deng from Waterloo, who will speak about the coarse bound conjecture. Please, Jintao, go ahead.
Okay, thank you for the invitation, and it's my great honor to talk about my recent result here. Today I'm going to talk about the coarse Baum-Connes conjecture. This talk is based on two papers. One is a joint work with Guo Liangyu and Qin Wang. Another one is joint work with Qin Wang and Benyin Fu, post recently. So before I talk about the coarse Baum-Connes conjecture, I would like to talk about what is the algebra, sister algebra we care about the most. So the algebra we will talk about in this conjecture is called the rule algebra. So rule algebra is defined for metric space. The metric space for simplicity, I'll just talk about the metric space with bounded geometry. So what's the meaning for bounded geometry? If you fix any radius r, you can always find a constant such that the number of the ball with radius r always has element less than the constant nr for all the elements in X. So for example, we can consider about X to be a group, a countable discrete group with word length metric, and this is the most interesting example. A second one is a connected graph. So if you have a connected graph, you define the metric to be the geodesic metric. So any 2 point has distance defined by the number of the edge joining them. Well, maybe this is unique, so you are going to take the smallest number. So this is the metric on the connected graph. And another example, also interesting, is you can take a discrete subset in a non-compact Riemann metric, a Riemann manifold. So while the Riemann metric on the manifold is proper, once we have such a Riemann manifold, we can take a subset, a dense subset. You can take the maximal one such that it's C separated for some constant C. While C separated means for any 2 point, the distance is bigger than or equal to C. Okay, so this is just like you can consider M equal to R. Well, you take X, the subset, to be Z, to be those integers. So this is your X. So those are examples we are interested.
But wait a little question. Does this C separatedness assumption guarantee that the geometry is bounded?
Oh, C separated. You can just take take any C separated and then take by the zone lemma. You can take the maximum one.
Mm-hmm. Yeah, but I mean, does this hypothesis guarantee that for any given R, the number of elements in the ball of radius R around every element has at most a bounded number of points? Or is that the combination of that assumption plus the discreteness?
Oh, this is just to choose a subset. It's usually you don't want the manifold to be weird. You just want the metric to be proper. So the meaning of the proper is every closed ball is compact.
Mm-hmm.
Yeah, so it's
so
like
compact and discrete implies the finiteness.
Mm-hmm.
Okay.
Yeah, and also bounded geometry, some more assumption. We just want some Yeah, we just wanna the remaining manifold is not that weird. It's just like
the bounded geometry is an extra assumption.
Yeah.
Ah, okay.
But, yeah,
that's what I was asking. Yeah. Okay.
Okay. Thank you for the clarification. Okay. So maybe it's easier way to understand such. You can think M is just some universal covering of a compact, a closed manifold. Closed manifold. Then actually you can take X to be the one orbit, some orbit in the universal covering. Yeah, this is just one orbit. So the one orbit is quite sorry. This should be one. Yeah. So this is the idea. This is the interesting example. I will talk about this later. Okay. Now we have such a discrete metric space with bounded geometry. Now we can define the row algebras. So for defining the row algebra, we need to fix some Hilbert space which is separable and infinite dimensional. Then once we have this Hilbert space, we can consider all the bounded operators on the tensor product Hilbert space. So for this tensor product here, for every bounded operator on this tensor product Hilbert space, we can express it as a matrix. So as a X by X matrix. And then, sorry, there is no gamma here. So each entry is actually a bounded operator on Hilbert space. Why you can do this? Because this tensor product can be expressed as a direct sum of those Hilbert space. So you can define, once you have the bounded operator T, you can define Txy for each xy. Okay, so the advantage of expressing every bounded operator as a matrix is you can easily understand the connection with global geometry of the metric space. So the most important concept is finite propagation. So what is the finite propagation? The finite propagation means the matrix is actually defined on a bounded width strap. So outside the bounded width strap, it's 0. So this is the propagation is defined to the largest distance xy on which Txy has non-zero entry. So you can view it as a matrix, and then you find a bounded width strap around your diagonal. So non-zero element always focus on this part, and outside is 0. Okay, so the diagonal one is actually has propagation 0. So you can the concept of propagation comes from physics. It's just like how far some signal can transfer. For example, if we have a bunch of islands in the sea, so if you have a signal and it was transported to another places, you use some machine. The propagation of the machine is how far the signal can transfer to. Okay, so if the propagation is small, then this is quite isolated, and this is the very important philosophy in the definition of localization algebra. I will talk about later. Okay, another important one is locally compact. Locally compact means for any bounded subset in X, if you consider about the operator defined by the multiplication by calculative function on A. If you multiply with T from the left side and multiply with T from the right side, both are compact operators, then you can say it's locally compact. Or equivalently, in this situation, you can say every entry is compact operator. So this situation
being bounded geometry. because
yes.
bounded is finite.
Yeah.
Okay.
Yeah. So this is much more simple, but this definition we actually need it later. Because we can also define everything here for the general metric space, not necessary to be discrete. Okay. So now we define the row algebra. So firstly, we consider a star algebra. So it's all the operators, boundary operators on the tensor product Hilbert space with finite propagation and locally compact. So this is a star subalgebra. And if you take completion under the operator norm, you will get the row algebra. So row algebra is very important in the application of in the application of coarse geometry to the question of topology and geometry. I will show that later. Okay, the question is so for this system algebra, we really care about this system algebra is very complicated. So firstly, it's non-unital, and secondly, it contains a copy of our infinity of x k. So this system algebra itself is very complicated. So in order to study this system algebra, we want to introduce the concept of K theory, because if you have this is not unital, but in order to talk about the K theory, we need to talk about the K theory for a unital system algebra. Then we use a trick to join a unit to the non-unital case. So if you have a unital system algebra, you can consider all the matrix algebra. You put them together by the inclusion. You can increase the size of n by n matrix to n plus 1 by n plus 1 just by adding 0. Okay, so you have all those matrix, and then you consider the projections in this matrix algebra, and we also want to module some equivalent relation. So this is definition of projection. So what is the definition for the equivalence? If you have two projection, they are equivalent if you can find some other operator in the matrix algebra. Maybe the size is a bit bigger than P and Q, and you will have V star V equal to the enlarged size P, and V star equal to enlarged size Q. Then under this equivalent, we will have an abelian semigroup. So with the addition P equivalent class plus Q equivalent class equal to PQ equivalent class. So this is an abelian semigroup, and so the abelian semigroup is not good enough for us, because it's usually semigroup is a bit harder to compute. So we can make it into a group which is called a Grothendieck group. So the definition, I will talk about the definition of Grothendieck by talking about the two examples. So for the first example, we have n, the integer, the natural numbers. By natural number, I mean all the natural number with 0. We talk about the 0. Okay. So the Grothendieck group of this semigroup is defined to be a pair Mn. So and module some equivalent relation. If you say M1, M2 equivalent to M2, N2, that means you can find some other integer k such that M1 plus N2 plus k equal to N2 plus M2 plus k. So essentially, what I'm doing here is so the difficulty in abelian semigroup is we don't have a minus, so we define the minus operation by a pair. So here Mn actually means M minus n. That's the reason we put it put it into a form of a pair. Okay, and similarly, you can find the Grothendieck group of n with infinity. This is trivial. Just because you can make this k, you can always make this k equal to infinity. Okay, so this is the difference. Okay, so and we also have the functor reality. If you have a homomorphism from A to B between the unitary system algebras, then we can define the K theory from A to B. So this is the definition for the unitary case. While for the non-unitary case, we just join a unit for this system algebra, and then we consider. So it's just A plus the complex number C, and then we have a quotient map from the we call this unitization to C. Well, the pair A lambda was mapped to lambda, and here the K theory is defined to be the kernel of, as I said, this is a star homomorphism, and the K theory is has functor reality. So you can define the star homomorphism. You can define the homomorphism between the abelian groups. So the K theory is actually defined to be the kernel of this homomorphism. Well, we can also define K1. The K1 is defined to be the K0 of the suspension. Well, the suspension is actually equal to C0R tensor product with A, and fortunately we have Baum periodicity. So if you keep taking suspension of A, if you take the multiple suspensions, actually it's so second. If you take suspension twice, it's just K0 of A. So 3 times is K1. So this is a periodicity with period 2. Well, interesting examples are the K theory of C, the simplest system algebra, equal to Z, and K0 of n by n matrices is also equal to Z. You can actually check the K theory of all the compact operators is also equal to Z. Well, so if you have a projection in K, so this identification is actually given by taking the trace, or if you have a projection, the K theory class of P is actually equal to the rank of P, so the dimension of the range, and the K1 of C and n by matrices and compact operator equal to 0, and also K theory of B of H equal to 0. This actually came from the example we talk about here. Okay, so this is the concept of K theory. The question is, how do we compute K theory? So in the algebraic topology, we have homology theory and cohomology theory. We always want to find some arithmetic to compute them. And here for the K theory, we also have our algorithm, which is called a Melville-Torres sequence. So it says if you have two ideas Ij such that A is the sum of Ij, then you have the 6-term exact sequence. Say so the advantage of this system exact sequence is so this is the K theory we want. Well, A, you can view it as it was a combine of two smaller algebra I and J. So if you know the smaller algebra I and J, if you know the K theory here, 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 and here, then you can use sublemma. You will get the K theory of A. So for example, if you make A equal to C0 of some locally compact space, and A has an open cover UV, you can view I equal to C0 of U, J equal to C0 of V. So the computation of K theory of C0W is actually equal to the K theory of I and J, and actually it comes from all the data of U and V. So that means if you want to understand the W, you just understand the building block of W and then glue them together. So this is the philosophy. And if we come back to the question we just raised earlier. So how do we compute the K-theory of the row algebra? So there is so the problem you may notice here. If you want to use Melville-Torres sequence, you definitely need some ideas. So so from this example, if you want to understand some space, you definitely need the building. You need to understand the building block of the space, right? And those. So for each building block, it corresponds to an idea. But the question is a subspace. So if you define the row algebra for the subspace, it's not an idea. So you can visualize this from the definition of the element in the row algebra. So if you consider a subset, if you have a signal in this subset, it always been transported outside. So so this tells you this system algebra is quite global. You cannot find the canonical ideas.
So
that's the reason.
Sorry, a question. Do you mean, is this algebra often simple?
Oh, and I'm not talking about simple. I'm just talking about. I'm not talking about it has no ideas. I'm talking about it has no canonical ideas to the subspace.
Mm-hmm. But is it?
Yeah.
But
so
in general, in examples, does it tend to be simple or purely infinite simple or not?
Oh, this system algebra always has an example. So it's compact operators on X.
Mm-hmm. Yeah, but compact operators are simple. That's why I ask.
Yeah, it always contain that system algebra. And sometimes it's also contain another idea. Yeah, this is a good question. It always contain another idea called a ghost idea. And only in the case when X has property A, these two ideas coincide. And the ghost idea, the ghost idea really connected to the counterexample to the surjectivity of Baum-Connes map. Yeah. So if you consider the groupoid system algebra associated with the coarse groupoid of X, then actually you can find some ideas from the boundary. So that's another very interesting question to find the ideas. But here I just want to emphasize that for any subspace, if you define the row algebra to the subspace, it's not an idea. That's the reason, even though you understand the building block of X, you still don't know what is the global geometry of X. So global geometry from that means you cannot glue the local data together.
May I ask you a question?
Mm-hmm.
If you take a subspace and then you just to forget those arrows that goes out from your subspace,
mm-hmm.
If you restrict to that subspace with all the arrows inside them, do you have an idea?
That's just a sub-algebra. It's not an idea.
I'm
just saying. If you consider the idea, you always take some operator to multiply with this idea, and then it will trans something out.
And then you go up. Okay, thank you.
Yeah. This is the disadvantage of this algebra. Okay, so the goal to understand the Baum-Connes conjecture is actually understand the K-theory of this system algebra. And now let's talk about the motivation in geometry and topology. Why do we care about the K-theory of the row algebra? So it has some applications in geometry. So assume, so it answers the question of the existence of positive scalar curvature on a manifold. So let me be explicit. So if you have a Riemannian metric, then we can define a scalar curvature. Once you have a metric, you can define a scalar curvature, which is a function, a smooth function defined on the manifold to R. And this is quite important. This is a quite important invariant for the Riemannian metric. For example, if you know the curvature, scalar curvature is smaller than 0, So it's look like this. If it locally, it might looks like this. So if it is equal to 0, locally it's like a cylinder. If it's bigger than 0, it's locally it's like a sphere. So if you know the even though you know the sign of the scalar curvature, you actually know quite a lot about the manifold. Okay, so the question is, if you have a smooth manifold and you are given a function, a smooth function, can we put a Riemann metric on M such that the prescribed such that the metric with the prescribed scalar curvature? So a very simple example is the N-torus. Well, this, even though this example looks simple, but the question, but it's super difficult. In 1970s, there are two groups of people. One group is Richard Schorn and Xintong Yao. Another group is Grumov and Lawson. They try to solve this problem in different methods. So eventually they give a negative answer to this example. Well, we are very interested in the approach of Grumov and Lawson. Let me talk about the baby version of their solution. So if you have a smooth manifold and closed means compact without boundary, we also further assume that we can assign, we can find a Riemann metric on M, and also it has a span structure. Well, span structure is just a structure a little bit stronger than oriented, just a little bit stronger than oriented. And with the span structure, we can define the Dirac operator. The Dirac operator actually is an bounded operator from L2 from a Hilbert space to another Hilbert space. Well, by the ellipticity of D, we know that D is a Fredholm. So what's the meaning for being a Fredholm? It means the kernel of D is finite dimensional, and the kernel of D star is also finite dimensional. So in this case, you can just define the Fredholm index of D to be the difference of those dimensions. And this is important index. And we also have the Lichtenauerwicz formula. If you take the square of the Dirac operator, is equal to Laplacian plus scalar curvature over 4 times identity. Well, you can view this as an operator on the between those two Hilbert spaces. Well, here delta is actually positive. Delta is positive, and if the scalar curvature is also positive, that tells you D square is a strictly positive element, which is invertible. So D square is invertible is the same thing as D is invertible. So invertible means that the Fredholm index vanishes. So here, then we have that if the Fredholm index is non-zero, then it's impossible to find the scalar curvature. Okay, so well, you may say the index of D is hard to compute because it's a differential operator. So find the Fredholm index is the same thing as computing the is the same thing as solving ODE. So it's quite hard. However, Atiyah single index theory tells us this index is equal to some A-hat genus. Well, this number is topological, and thus is very computable. So, however, so this is the idea comes from Atiyah single index theory. However, this idea still does not give an answer for the example when M is equal to the N-torus. The reason here is it's Tn is too flat, so it's A-hat genus equal to 0. Well, that means we need to find a better index. Well, the philosophy works. So if we can find a better index, then we can follow the idea above. So here it's called the higher index. Well, now we just consider the universal covering. Well, the universal covering, we can choose a discrete subset. As I said, you can make the discrete subset as an orbit of the fundamental group. Okay, so then we can, once we have this subset, we can lift D, the Dirac operator on M to the Dirac operator on the universal covering, and then the Hell index of D tilde is actually an element of the K-theory of row algebra. Okay, so and again, the previous ideas still work here. If the Hell index does not equal to 0, then we still can claim that no positive scalar curvature metric on M tilde. As a result, M has no positive scalar curvature, because this positive scalar curvature we consider actually is a lifting of the positive scalar curvature metric on M.
So sorry, did you give an idea of what the higher index of delta D tilde is? It's not the normal index of D tilde, or is it?
Oh, so here I'm just talking about the philosophy of Hell index. So you can define. We know D tilde is called a Hell index just because D tilde is not Fredholm anymore.
It's not Fredholm anymore. Okay.
Yeah, but still, if you take the point view from the Hilbert module, it's Fredholm in some sense. If you module something. Oh well, wait, not Hilbert module. I'm sorry, just a module something. So you can get the concept of the generalized concept of Fredholm, and it's the same thing to consider the K-theory.
So is there an ideal so that the index map associated to the ideal is this higher index?
Oh, if you consider the action of the fundamental group on X, and you use the trace mapped to K-theory. This is actually the gamma index of RTL. Well, yeah. Well, here the important, the crucial point is if the RTL single the Fredholm index does not work, you can generalize it to a better index. Well, you have to the price you are going to pay is you are going to consider a harder K-theory. Yeah, this is a problem. This K-theory is much harder to compute, as I explained. Okay, actually the philosophy is the same here to compute it. So for the Fredholm operator, we know it's hard to compute, but we can find some topological group, and we use the idea from topology to compute it. And the same thing for the Hell index, we can still find some topological thing to compute the K-theory of this sister algebra. So this algorithm is called a Baum-Connes conjecture, or if you consider the group action, this is called equivariant Baum-Connes conjecture. So now let's talk about the computation. So we wanna, because X is discrete, so we wanna make it continuous. So we just formally consider the Rips complex at scale D for each number D. And this is a topological space, and it also has a metric, which is called a spherical metric. The idea to put a metric, the spherical metric on this Rips complex, just because we want a PDX looks like X from a far distance. I will talk about this later. What does it mean by looking at this space from a far distance? And then we can choose we can define the rule algebra for the Rips complex. Actually, it follows from the situation in discrete. Okay, and then the point here is we can define a sister algebra called localization algebra. So this is just the collection of paths on the half-wheel line to the rule algebra. To the rule algebra, and you want this path to be uniformly continuous, uniformly bounded, and the most important, propagation smaller. Propagation could be very smaller, could be very small as t goes to infinity. So this is a crucial point in the definition of localization algebra. And then you take completion under the sup norm, you will have the localization algebra. This was actually defined by Yu. So, and then from the localization algebra to the rule algebra, there is a natural evaluation as zero map. And if you consider all the scale of Rips complex, you take the inductive limit, you will get the assembly map. This is how do we define the easiest way to define the assembly map. Well, later I will show why this is crucial. Okay, the Baum-Connes conjecture claims that this assembly map is an isomorphism. If you consider the group action, you just add one condition, which is called a gamma invariant. Then this is called the equivariant Baum-Connes conjecture. Okay, the known result for this conjecture is the most important one is X is cos-embeddable into Hilbert space. Then the Baum-Connes conjecture holds. This was a result by Yu in 2000. The example of this cos-embeddable into Hilbert space includes a amenable group, 18 amenable groups, hyperbolic groups, exact groups. So all of those next groups are examples of cos-embeddable into Hilbert space. I will talk about the definition later. Okay, so now let's talk about the go back to the obligation problem. So if you have a Dirac operator on the universal covering of M, and you actually can define a localized higher index in the key theory of the localization algebra. And if you consider the image of this key theory class under the evaluation as zero map, this is exactly the higher index. Okay, so if this gives you the same, if this is an isomorphism, this tells you the local index is actually the same as higher index. And the advantage of here is the key theory of localization algebra is very computable. So that's the result. It's easier to understand the localized the local higher index. But why this is computable? Just because if we consider a very simple case, we have those separated subset. We have the separated subset. Then because the localization algebra consists of all the paths with small propagation. If you have operator with small propagation, that means you cannot transport your signal to the other part. So there is no communication between those isolated subset. It's very localized. This is one reason. The second reason is we will have Melville-Torres sequence. So it's purely topological. It's localized, so it's computable. That's the reason we care about the Baum-Connes conjecture. Well, this depends. This conjecture actually depends on the large scale geometry of the underlying space X. Now let's talk about the cos geometry. So Gromov defined the cos embedding. If you have two matrix space, a map between them is cos embedding. If you can find the two non-trivial and non-degenerate function defined on the half-real line, the image of the distance between the image of any pair is actually controlled by the pre-image. You will see this is cos embedding. So a good example for cos embedding is you embed Z into R. This is isometric. And from the larger scale, X and Y is cos equivalent if Y is equal to some R neighborhood of the image. So here, Z is cos equivalent to R. So this is the philosophy of cos geometry. We always think about if we go back to the calculus, you'll notice that in calculus we actually worry about the continuity of a function. Well, it's just like you are enlarge everything. You want all the details from the small structure. Well, there is a disadvantage here. You will lose the big picture. For example, if you replace, I think most people have a pair of glasses, including me. If you replace your glasses as a microscope, then you can see everything on everything outside. But the question is, can you find the way home? Well, you will get lost, definitely. Okay, so another good example is if M is a closed manifold, then you consider the fundamental group. The fundamental group is actually cost equivalent to the universal covering of M. The most important case is Y equal to a Hilbert space. Then X is called cost embedding into Hilbert space. And the geometry in the Hilbert space is quite simple. So it's just like you will put the metric space you are considering into a nested object, and even though in the process of throwing your space into the Hilbert space, you will lose some local structure, but the global picture was preserved. So just like you are standing in front of a mirror, but the mirror is a little bit blurred. You cannot look very your face is not that clean in the mirror, but it still tells you a lot of information of you. Okay, so that's the reason why we really care about the cost embedding into Hilbert space. Well, this includes a lot of groups. So for example, the amenable, amenable, exact, and the group. So it's the same thing as group with property A, and hyperbolic and finite asymptotic dimension. So these are examples of cost embeddable. Well, we also have a counterexample. Gromov found that expander is actually counterexample. Well, this is a definition of expanders, but I'm not. Oh, sorry, but I'm not going to the details of the construction. So it's just you can view this as a union, or you put a bunch of finite connected graph together, and the graph is become bigger and bigger, and also those degree of those finite graph are bounded. And while there is a constant called Chigger constant, will be away from zero. That means it's sparse. However, the connectivity connectivity of the graph it remains very strong. Okay, and the cost then actually the cost disjunct union is you just formally put a metric on the union, and then on each component is equal to the original metric, and the more important, the space between those components become bigger and bigger. So this is the idea of the disjunct union. The construction of expander, the first example is given by Margulis. He considered the property T group, which is rigidity finite, means you can find a series of normal subgroup where each of them have finite index, and the union of those normal subgroup equal to identity. Then the finite quotient are actually a family of the expander. This is a quite important example. And by Haysen, Scandalis, and Laforgue, they proved this is for the coarse Baum-Connes conjecture does not hold for a class of expander, and you can also find the proof in Rufus Billet and Guliang Yu's paper. Okay, so a very natural question is, we know expander cannot cost embedding into Hilbert space, but you may ask if the expander is the only obstruction to the cos-embeddable into Hilbert space. So Arzhantseva and Tessera constructed a weaker version of expander, which is called a relative expander, and he found that this expander, weaker expander, does not contain an expander, yet it does not cos-embeddable. It does not cos-embedding into Hilbert space, and it's an obstruction to cos-embeddable into Hilbert space. And also, they show that the cos-embeddability of a metric space is not preserved by taking extension for group. So be precisely, if you have an extension of discrete groups, if you assume n is cos-embeddable and the quotient group also cos-embeddable, and you may ask if G is cos-embeddable. The answer is no. So you may ask, what about the cos-Baum-Connes conjecture for this G, and the cos-Baum-Connes conjecture for the relative expander constructed by Arzhantseva, Tessera, and actually Dalabi and Hukru also has the construction of a relative expander. Well, we answer this question positive. So if you have an extension, we assume, if we assume the normal subgroup and quotient group admit cos-embeddable into Hilbert space, then the cos-Baum-Connes, then the equivariant, this should be G, this also should be G. This is isomorphism. Well, that means cos-Baum-Connes conjecture holds. Well, if you consider the equivariant version, then this is injective. So which means the Novikov conjecture also hold. And another result by me and Qin Wang and Guoliang Yu, we see that if you have a sequence of extensions by finite groups, and you assume the quotient, the cos-disjoint union of the quotient admit a cos-embedding into Hilbert space, and the cos-disjoint union of the normal subgroup has property A, then we can verify that cos-Baum-Connes conjecture holds for the cos-disjoint union of Gn. Actually, all the construction of relative expander has this structure. The union of n of the normal subgroup has property A, and the union of quotient group admit cos-embeddable into Hilbert space. Actually, there are examples more easier. They just wanna each of n is amenable. Is abelian. As a result, is amenable. Well, probably A is a generalization of amenability. Well, we can also consider the equivariant case of the cos-Baum-Connes conjecture. So if you have a group action, which is we just consider for simplicity, we consider free. Okay, so we want this action is proper, free, and by isometry. Proper means the group action will transport each point to infinity. It will never come back. And action by isometry means the distance between gx and gy remains the same as distance between x and y. That means the action does not change the distance. So free means for any point, the stabilizer is just the identity element of the group. Here you can define the equivariant row algebra to be finite propagation, locally compact, but here you add one more condition, which is gamma invariant. Well, T is a matrix, and gamma invariant means the entry on gx gy equal to the entry on xy. Well, here Hilbert space H has a trivial action of gamma. Then you can follow the same thing as what we did earlier. So you have the evaluation as zero map, and then you put all those Gibbs complex together, you will have the equivariant assembly map. Well, equivariant cos-Baum-Connes conjecture claims this is isomorphism. Equivariant cos-Novikov conjecture claims this is injective. Well, recently we posted a paper on some cases of equivariant coarse-Baum-Connes conjecture. So if you have X, a metric space with boundary geometry, gamma, a countable discrete group, the most important assumption on this gamma is minimal, and you also assume the action is proper by isometry, and for the quotient map from X to the orbit space, each fiber are uniformly cost-equivalent to each other. Well, then we can assume the quotient space meet cost-embeddable into Hilbert space, meet cost-embedding into Hilbert space. So the conclusion is that the equivariant coarse-Baum-Connes conjecture holds for this action. That means the equivariant assembly map is an isomorphism. Well, if the action on the metric space is co-compact in the sense the quotient is finite, then this is nothing. This is just the Baum-Connes conjecture for the group gamma. So you can this actually this in that case this result is just the Baum-Connes conjecture for amenable groups. Well, the Baum-Connes conjecture, I think at this moment the best result for the Baum-Connes conjecture is actually for the group is the group which has amenability by Hickson and Gasparov. And also there are some extension result by Oyuno in the Baum-Connes conjecture. Okay, that's all.
Okay, thank you very much. So, are there any questions from the audience?
Maybe why? Where do you use that the action is free? You cannot handle, for example, finite stabilizers or something like that.
Oh, the free. You're asking why this action is free, yes. Right? Oh, yes. Just because actually you don't need a freeness to define the equivariant algebra, but if we take freeness in account, then the definition of gamma inversion is quite simple. Otherwise, you have to consider, you have to worry about the, you have to replace the tensor product Hilbert space as L2 of X tensor with L2 of gamma tensor with H. So gamma equivalent will becomes TGXGY equal to the G conjugate on XY. This is just this may be a little bit more complicated. So that's the reason I put an assumption on freeness, but actually it's not a big deal.
Okay.
Okay. Just because if it is, yeah, if it is not free, then if you still use this definition, for gamma invariant, you will miss some information of some torsion group, or a stabilizer. Okay.
Okay, thank you.
I wanted to ask something. So in all cases of the results you stated, you had that you know I mean, you had some decomposition into pieces.
Yes.
In which you knew the conjecture in the pieces, and then you glued them together somehow.
Yes.
Could you give a rough idea in one of the examples, at least, of how this is achieved? Is it a Meyer-Vittori's argument, or what is involved? What are the techniques involved?
Okay. Yeah, this is maybe let's consider let's consider some naive example. So if you have a metric space X and we consider the system algebra of C0x. Well, I still want x be discrete with bounded geometry. And now let's talk about the twisted rule algebra. So this was defined as this. So here, so all the element is the x by x matrix, and we know txy is in C0 of x tensor with k. Tensor with k is just make sure it's cost equivalent. So secondly, we want a finite propagation. That means txy equal to 0. There exists some r bigger than 0. Tx such that txy equal to 0 if distance between xy is bigger than r. And
wait a second. Is x is just the good old metric space with bounded geometry?
Yes.
So C0 of x is, I mean,
is
like
a function. Yeah, you can view it's a
since x is discrete. Yeah, it's like if x is countable, their sequence is going to 0.
Yes.
Infinity. Mm-hmm.
Yeah, vanishing at infinity.
Mm-hmm.
Yeah, I don't want to make it as a sequence. Just think as a function. That's easier to. It's the same thing, but easier to express the idea.
Mm-hmm.
Okay, the most important is here. This is a crucial point in the cutting and pasting. So we consider the support of the entry. You can find some r such that the support of the entry xy is contained in some r ball or in the ball centered as x with radius r. This is very important, right?
So is that for every x and y?
Yes. So here you can view the element is as a matrix, right? And it was supported on a strap with bounded width, and on each entry it's a function on x, right? But we consider the support of the function contained in the r ball of x. So this is very important. Yeah. So this is the idea to. So now let's say since the rule algebra of x has no canonical ideas, this is the problem. But however, now we know C star of x C0x, excuse me, has ideas, has canonical ideas. Okay, let's see why. So actually the ideas comes from the coefficient C0 of x, right? Because each subspace of x is will give you an idea of C0 of x. Mm-hmm. And if you restriction of the support, you will have an idea, right? The most natural one is what if we fix x0? Fix x0 in x, and we consider the direct function on x0. We just want some matrix from the twisted rule algebra. However, you want txy is always equal to some number term, some constant times this x this Dirac function? What if we want this? What if we want this the special element? Then by the definition of twistness, you will say Txy is just some matrix defined on not a bounded strap. It's just on a bounded subset of xy, x times y, x times x. Sorry. So this means. So the matrix. This means you can find some r bigger than 0, such that Txy is a finite matrix. So well, that means so Txy is supported. Sorry. So Txy is equal to 0 if x or y are not in the arbor of x0 times arbor of x0. Well, by boundary geometry, this is the reason why we need the boundary geometry in the cutting and pasting machinery. So it looks like this. This is a purely finite matrix, and actually, actually you can check the twisted row algebra is actually you put all this finite matrix together, and K theory of finite matrix is very clear, right? So it's understandable. So this is a philosophy of cutting and pasting. Well, there is an issue here. How do you remove this coefficient? The question is, we introduce this to the proof, but how do we remove it? The idea is, what if C0 of x just looks like, on the key theory, it looks like the continuous function, C0 function on R. So, and also the issue here is C0 of R reflects no geometry of x. That's the problem. So even though we and the K theory here is quite. I'm sorry, I shouldn't say K theory the same. I should say the K theory of C0x is non-trivial. So we introduce this, we will get some trouble. And what if we can replace C0 of x with some trivial K theory thing? Well, the best candidate is C0R. Well, C0R reflects no geometry of x, but by the Baum periodicity, we know this is on the K theory. This is exactly the same as some system algebra introduced by Higgs and Kasparov-Trott, and also this reflects the geometry of x just because you can embed C0 as C0x into the center, the center of the multiplier algebra, multiplier algebra of this system algebra. So here we know we have a system algebra. Firstly, does not change the K theory. Secondly, reflect the geometry of C0 of x. So this is the philosophy of cutting and pasting.
Okay, thank you.
Okay.
So are there any further questions? So if not, we thank Deng again, and let us stop the recording.